Hi, hello to all. I would like to introduce myself first. I am Dr. M. Siva Prasad, currently working as a Associate Professor of Chemistry in Marri Laxman Reddy Institute of Technology and Management. Today in this session, I am going to inculcate engineering chemistry topics. In engineering chemistry, there are 5 modules are there. Number 1, water and its treatment. Number 2, battery chemistry and corrosion. Third one, polymeric material. Fourth one, energy sources. Fifth one, engineering material. So in this session, I am going to inculcate the first chapter, water and its treatment. So in this connection, in the first chapter, there are different topics are there. The contents are hardness of water, causes of hardness, types of hardness, how to estimate, determine the hardness, units of hardness. Next, potable water and steps behind the purification of potable water. Next, boiler troubles, reverse osmosis. Next, numerical problems. These are the contents of first chapter, that is water and its treatment. Next, so we know that water is most abundant, wonderful thing on this planet. Without water, we can't survive on this planet. So, so in our since from primary classes to here, we know that the water is unevenly occupied on this planet. 3/4% of water occupied in ocean and glaciers, river water, ponds, bore wells, canals, etc. So in this fresh water, usually contaminated with some impurities. So what are the impurities? In generally, the impurities are classified into 3 types. Number 1, physical impurities, chemical impurities, and biological impurities. Now coming to the point, physical impurities. So when we observe the water for drinking purpose or other applications, maybe industrial applications, agriculture related, whatever, first when we observe the water, if color, turbidity, taste, odor is there, that may not be useful for drinking purpose. For example, color. When we observe the water, if color is appear, maybe some metals or carbonates or sulfides are dissolved or present in this water, in that water. Next, turbidity. Turbidity means maybe clay or mud or sludge dissolved in the water. Next, taste. If the water having some taste, bitter taste, it may be contaminated with some different salts. Odor also may be that may not useful for drinking purpose. So these are the physical impurities. Next, chemical impurities. So chemical impurities again classified into 2 types. We know that inorganic impurities and organic impurities are chemicals. So inorganic, again there are 2 types, anion and cation. So coming to the point, cations is a positive charge ions, maybe some metals, aluminum, calcium, magnesium, ferrous, zinc, copper, etc. Next, coming to the anion, is a negative charge ion. It may be calcium, fluorine, sulfides, nitrites, carbonates, bicarbonates, etc. are dissolved. Next, organic chemicals. Organic chemicals means pesticides, petroleum related products, detergents, dyes, etc. These are the organic impurities. So here I incorporated, you can see anion, cation and organic related impurities. Next, the final one is biological impurities. Biological impurities mean maybe some living creatures, viruses, bacteria, pathogens, next parasite worms, etc. are present in the water. So again I am repeating, the impurities are three types. Number one is physical impurities, number two chemical impurities, number three biological impurities. In physical impurities, odor, taste, color, turbidity. In chemical impurities, inorganic, organic. Biological impurities, pathogens, bacteria. It's finished. Next, causes of hardness. So what is the root cause of hardness? Because of the water flows across the rocks on different soils. That's why maybe some impurities like sulfides, chloride, nitrites are there that dissolve this type of impurities. That's why the hardness is causes to the fresh water. So again hardness. So when we define in a simple way, very common definition is what is hardness. So hardness means if the water gives lather with soap is called as soft water. The reverse process, if the water doesn't give lather with soap is called as hard water. You can see lather means just like farming. So hard water, if it doesn't give lather with the soap is called hard water. For example, here I incorporated one chemical reaction. You can see soap, sodium stearate react with water, then it will form stearic acid plus NaOH. So here lather is obtained. Next, hard water. So the water which doesn't give lather is called as hard water. Already I discussed, I explained. So here you can see sodium stearate and hardness causes salt. It gives insoluble contaminants. So this is called hardness. Again I am repeating, hard water, soft water. Hard water means that if the water doesn't give lather with the soap is called as hard water. If the water gives lather with soap is called soft water. Finish. Next, types of hardness. Number one, temporary hardness and permanent hardness. What is temporary hardness? So simply I will explain in a simple way, easiest way to remember what is temporary, what is permanent. Please listen carefully and remember it. Temporary hardness, if the water contaminates or dissolves or having or present calcium, magnesium bicarbonates is called as temporary hardness. So again I am repeating, what is temporary hardness? This is also very important question. So again I am repeating. So temporary hardness, if the water dissolves, presents or contaminates or having calcium, magnesium bicarbonates is called as temporary hardness. You can see calcium bicarbonate or magnesium bicarbonate if present in the fresh water is called as temporary hardness. So you can see here chemical reaction. So the temporary hardness can be largely removed by boiling method. So here you can see, here I incorporated two reactions. Calcium bicarbonate, when heating, calcium divided into calcium carbonate and H2O and as well as CO2. Similarly, magnesium bicarbonate. This is temporary hardness. Next, second one, permanent hardness. It is quite opposite to first temporary hardness. Here, except bicarbonates means if the water presents having or dissolves or contaminates with chlorides, fluorides, sulfides, nitrites, carbonates is called as permanent hardness. So here you can see, here I incorporated calcium chloride, magnesium chloride, calcium sulfate, magnesium sulfate, ferrous sulfate, and aluminum sulfate. So again I am repeating, permanent hardness is if the water dissolves or presents or having or contaminate with sulfides, chlorides, nitrites of calcium and magnesium salts. So permanent hardness cannot be removed by boiling method like temporary hardness. There are different methods are there to remove the permanent hardness. Maybe internal treatments or external treatment, maybe some other treatments are there and available. So total hardness. So total, how to calculate total hardness? So temporary hardness plus permanent hardness is called total hardness can be calculated, will be calculated. Next, what are the units of hardness of water? There are 4 types of units are there. Number 1, ppm, milligram per liter, degree of Clark degree or degree of French. So here you can see incorporated here parts per million, ppm. So the number of parts per calcium carbonate equivalent to hardness present in 10 to the power of 6 parts of water. So 1 part calcium carbonate equal to 10 to the power of 6 parts of water. Similarly, milligram per liter. So 1 part calcium carbonate equal to 1 liter of water. Similarly, Clark's degree, it is equal to 7 into 10 to the power of parts of water. That means 1 part of calcium carbonate equal to 7 into 10 to the power of part of Clark degree. Again, similarly, degree of French. So 1 degree of French equal to 1 part of calcium carbonate equivalent to 10 to the power of 5 parts of water. So here I incorporated relation between water of hardness. So 1 ppm equal to 1 milligram per liter equal to 0.1 degree of French equal to 0.07 degrees of Clark. So again I am repeating, please remember there are 4 units are there, and generally number 1 ppm, parts per million, 10 to the power of 6. Next, milligram per liter. Next, Clark's degree, 7 into 10 to the power of parts, 7 into 10 to the power of 4 parts. Next, degree of French, 10 to the power of 5 parts. This is also similar to parts per million. Next, so numerical problem is there. So it is very simple formula. Weight by molecular weight of calcium carbonate into 100. So when given values are there, if you substituted the values in this formula, it can easily calculated. So it's very easy. Just remember this formula: weight by molecular weight of calcium carbonate into whatever calcium carbonate or calcium sulfate into 100. So it's very simple numerical problem. Next, estimate. How to estimate, how to calculate, how to determine hardness of water. So especially there are different types of titrations are there. So before going to discuss about complex symetric titration, we have to know how many types of titrations. There are in generally 5 types of titrations are there. Number 1, complex symetric titration, redox titration, replacement titration, precipitation titration, and acid-base titration. Here among them, here complex symetric titration is more significant and also it plays more significant role in complex related to chemicals determination. So in complex symetric titration, EDTA plays a significant role because of it can form stable complexes with metal ions and also accurate determination of their concentration. That's why EDTA plays significant role in complex symetric titration. It is also hexadendent ligand, EDTA. That's why very commonly, very generally used in complex symetric titrations. Next, complex symetric titration in form of allometric analysis. Here, colored complex are used to indicate the end point. For example, methyl orange indicator, phenolphthalein indicator, EBT, etc. indicators are there. So especially in complex symmetric titration, here we are using EBT indicator. EBT means iriochrome black tea. Next, so here I incorporated the structure of EDTA. So ethylene diamine, EDTA full form, ethylene diamine tetraacetic acid. You can see diamine, these four tetraacetic acids, ethylene diamine tetraacetic acids. So in this complex symmetric titration, especially there are 3 steps are there. Number 1, first step. First, we have to prepare EDTA solution and MgSO4 solution in a concern standard flasks, maybe EDTA half liter or 1 liter, and MgSO4 in 100 ml standard flask. So pipette out this permanent cause salt MgSO4 into conical flask, a conical flask. Then we have to add 5 ml buffer solution, then EBT indicator. After adding EBT indicator, the color will be formed as a wine red color. So after getting wine red color, we have to titrate with the EDTA. So up to concurrent values, we have to conduct the experiment. We have to repeat the experiment. So then we have to note down the values up to concurrent values. So again I am repeating. In the first step, we have to prepare EDTA, MgSO4. EDTA will take burette, MgSO4 20 ml of MgSO4 pipette out into conical flask. Here I incorporated, you can see 20 ml of MgSO4, 5 ml buffer solution. Next 1 or 2 drops of EDTA indicator. Wine red color will appear. The titration with EDTA up to 3 times. 2 concurrent values. The 2 means concurrent values will come. The wine red color will convert it into blue color. Change into blue color. Then we have to write down the values. Then formula, when M1 V1 equal to M2 V2, we can calculate M2 value. Next, second step. We have to prepare pipette out 20 ml of tap water into conical flask. Then add 5 ml of buffer solution. Then EBT, 1 or 2 drops of EBT. Wine red color will appear. Finally, we have to titrate with EDTA. Wine red color will change to blue color. The values will be calculated. Write down the values. Wine red color changes to blue color. So wine red color, here I incorporated wine red to blue color. So again I am repeating, 20 ml of tap water, 5 ml buffer solution, 1 or 2 drops EBT, wine red color appear, then titrate with EDTA, wine red color changes to blue color. So values are to write down, then calculate M2 V2 equal to M3 V3. So M2 V2 we know already, previous step. We have to calculate M3. Next, final step. Instead of MgSO4 and tap water, we have to pipette out hot water into conical flask. Again 5 ml buffer solution, 1 or 2 drops EBT, then titrate with EDTA. So wine red color to blue color will change, will appear. Then we have to calculate, we have to note down the values, then calculate M3 V3 equal to M4 V4. So finally we will get temporary hardness, permanent hardness and total hardness. So these three steps are more important in complex symmetric titration. So here, what is the main role of buffer and EBT? Buffer means acid-base mixture. Here you can see I have incorporated NH4Cl and NH4OH. This is also one of the combination of a buffer. So there are different types of buffer. Bretton-Robinson buffer is there, acetate buffer is there, citrate buffer is there, phosphate buffer is there. In complex symmetric titration, ammonia buffer plays significant role. Next, so what is the role of buffer? we have to maintain the constant pH. That's why we are using a buffer solution. So maybe if we didn't use buffer solution, maybe the room temperature, maybe other foreign ions may contaminate the reaction mechanism. That's why buffer plays a significant role. Indicator EBT, so the color appearance is more important. So here EBT, Reochrome black tea. Next, specification of potable water. So potable water means as usual drinking water, potable water. So the name is derived from maybe potable water, potable water. So potable water, here I incorporated the total dissolved salts of potable water must not exceed 500 ppm. Next, the water must be free from heavy metals like lead, arsenic, chromium, etc. metals. Next, the water should be clear, colorless, odorless, turbidityless, and pleasant taste. Next, the optimum hardness of water must be 125 ppm. Next, the pH of potable water should be 7 to 8.5 pH. Next, the turbidity in drinking water should not exceed 25 ppm. The water must be free from pathogenic bacteria. Next, and also the water must be free from dissolved gases like hydrogen sulfide, carbon dioxide, and ammonia. Here you can see. So again I am repeating, this is the most important question also, and every exams it will come. So what is the specifications of potable water? Number 1, total dissolved salts in potable water must be not exceeded 500 ppm. Next, the water must be free from heavy metals like lead, arsenic, antimony, chromium, manganese, etc. The water should be clear, colorless, odorless, tasteless. It will be pleasant. It should be pleasant. The hardness of water must be optimum 125 ppm. The pH should be between 7 to 8.5 pH. Turbidity should be less than, not exceeded 25 ppm. Free from pathogenic bacteria and free from dissolved gases like H2S, carbon dioxide, and ammonia and other gases. Next, steps involve the treatment of potable water. Steps involved in the treatment of potable water. There are 7 steps are there. First, collection of water, the source of water, screening, aeration, sedimentation, coagulation, filtration, disinfection, and or sterilization. There are 7 steps. Again I am repeating: source of water, screening, aeration, sedimentation, coagulation, filtration, and disinfection and sterilization. First, in the first step, screening. The water passed through screening having larger number of holes, just like a net. So it retains floating of impurities like wood. You can see wood, pieces, leaves, heavy objects can be removed in this step. The first step, screening. Next, after getting screening, next step is aeration. Aeration means the water is then subjected to aeration. Means passing air through the water. So in this step, maybe some salts, some gases can be removed, like you can see H2S, CO2, and ammonia, carbon dioxide, ammonia can be removed in aeration step. Next, sedimentation. Sedimentation means to keeping the water without turbulence, without disturbance up to hours or days. The contaminants or impurities will down to the bottom of the vessel or tank. So here some type of impurities can be removed in sedimentation step. Next, coagulants. So after getting sedimentation, still if there is any impurities in coagulation step, we can easily remove the hardness causes impurities. For example, here you can see coagulants like alum, sodium aluminates and aluminum sulfates are added, which produce gelation and precipitates called flux, FLOCK flux. The flux attracts to helps accumulation of the colloidal properties, resulting in setting other colloidal particles. So after getting sedimentation, we have to add some coagulants like alum, sodium aluminates. So still there is any impurities, the both are reacted and separated. This method is coagulation. Next, filtration. We know that it is as usual filtration. So since for many centuries, this technique has been used. First, large particles, then sand type, next grain, next coal. Step by step, the filtration will be occurred. Finally, the fresh water will we can filter. So here you can see in the figure, inlet, sand, gravel, under drain. So the outlet, the final purified water, potable water will be, we will get the purified potable water. Next, disinfection of water. In disinfection of water, there are three types of there: chlorination, chloramine, and bleaching powder, and ozonization are there. So you can see here, in this step, sterilization, the process of destroying the harmful bacteria is known as sterilization or disinfection. You can see sterilization or disinfection, destroying the or killing the harmful bacteria. Initially, chlorination. So the process adding chlorine to water called chlorination. So it's simple, passing chlorine gas, so that can kill bacteria easily. So this is also one of the disinfection and sterilization method. You can see the here I incorporated reaction mechanism. When passes chlorine to the water, it react and forms HOCl, hypochlorous acid, and HCl. So these hypochlorous acid plays a significant role. Then it is divided into HCl and nascent oxygen. So nascent oxygen plays a significant role to kill the bacteria. It is a good oxidizing agent. So again I am repeating, chlorination. When passing the chlorine gas to the water is called as a chlorination. Here chlorine react with the water, it forms HOCl. Again HOCl divided into two parts, HCl and nascent oxygen. Nascent oxygen can easily kill the bacteria. Next, so in the disinfection or sterilization, our aim, our theme, our goal is to get the nascent oxygen. Then it is easily kill the bacteria. It will easily kill the it can easily kill the bacteria. For example, here you can see next step, adding of chloramine. Chlorine plus here you can see chlorine and ammonia. Chloramine will form, and then chloramine react with H2O. Then ammonia and hypochlorous acid will form. Hypochlorous are divided into HCl and nascent oxygen. So we know that nascent oxygen can easily kill the bacteria. It is a very good oxidizing agent. Next, ozonization. This is the most expensive method. So this is also one of the important method, ozonization. So ozone is a unstable, but it gives nascent oxygen. So here you can see O3 gives rise to O2 plus O, nascent oxygen. Nascent oxygen can kill bacteria. So disinfection or sterilization method, there are three: chlorination, chloramine, and nascent oxygen. And finally, by adding bleaching powder. So you can see bleaching powder react with water, calcium hydroxide will form, and chlorine and hypochlorous will be released. So again hypochlorous dissociated are divided, split into HCl and nascent oxygen. So Nascent oxygen, we know that it kills bacteria easily. So nascent oxygen, a strong oxidizing agent, monoatomic in nature, highly unstable, kill bacteria effectively. Okay, these are the steps behind potable water, involved in the potable water. Next, these are the references, engineering chemistry references, Ramadevi ma'am, and next Jain and Jain, next Sikka Agarwal, Cambridge, next treatment of potable water by Denver Water. These are the half of the syllabus I have explained. In the next class, I'm going to inculcate boilers and boiler troubles and how to purify the determine the boiler troubles. Next class I'm going to discuss. Thank you.